The binomial theorem lets us use combinations and simple patterns to quickly find the expansions of binomials raised to different patterns. This is the equation for the binomial theorem. Here, this is n choose I, just like we saw when we did our probability units. So let's try and expand the following x plus 2 to the exponent 5. This would be tough to do by hand, but what we're going to do is expand using the binomial theorem. So let's start over here. So our first term is going to be 5, choose 0, because that's where our counting is going to start with. Then I'm going to have my a value raised to the exponents n minus I. And then I've got my b, which in this case is 2. So we've got 3 pieces. To the exponent 0 here. And this is just coming from pulling the pieces from my expansion here. My next term, now I'm changing my I value to 1. So I would have 5 choose 1, x to the 5 minus 1, and then 2 to the 1. I'm going to keep going. So 5 choose 2, x to the 5 minus 2, 2 to the 2. I keep going. 5 choose 3, x to the 5 minus 3, 2 to the 3. And then I've got 2 more terms. 5 choose 4, x to the 5 minus 4, 2 to the 4. And then I've got 5 choose 5, which would be x to the 5 minus 5, and then 2 to the 5. So when I evaluate that in my calculator, I would get x to the 5 plus 10x to the 4 plus 40x cubed plus 80x squared plus 80x plus 32. And that's just evaluating the numerical part of each term and then the exponent that's on the x. So that is finding the entire expansion. We can also find a binomial in particular in that expansion, and we usually use this notation UR to represent the rth term. Okay, what we can do is find the general term or the next term. We would have n choose r here. We've got a to the n minus r and b to the r. That's just sort of an extension from our binomial theorem up here. We would have, okay, so let's try an example doing this. So we've got the 8th term in the expansion. Okay, I'm going to identify my n, my a, my b, and my r. And if I'm looking for the 8th term, this is u7 plus 1. So that means u7 is going to be my ur term in this case. So let's take my pieces of the equation. So my left side is ur plus 1, which is u8. That's what I'm looking for. That's going to tell me that my n value is 11, r is 7, my a raised to the exponent n minus r, and then my b raised to the exponent r. So now I've got 11 choose 7, which should give you 330. I've got x to the 8, and then this should give me minus 78,125. Multiplying those all together gives me minus 25,781,250 x to the 8 as my 8th term. Okay. The other thing that we can do is work backwards here, and we're going to find the coefficient of the term in the expansion that contains x to the 21. So working backwards here, our first step, we do need to find out what r is equal to. In my expansion, the parts that I care about are the parts that have an x to them. So I'm going to substitute in my general a and b and raise to the exponent. The 2 I'm ignoring because it's just a number, not a variable. And then I'm going to put in what I know here. So I've got my n is 13, my r I don't know, and then I've got r here. But what I can do is I can combine those expressions. So 39 minus 3r plus r. And now I've got an expression for x in terms of r up here. I can then set that expression equal to x to the 21 because that is the exponent that I want on my term when I solve it. So that means because my bases are the same, I can accept the exponents equal to each other. And then this will give me r equals 9. So therefore, I'm looking for that 10th term. What I need to do next is actually find that 10th term. So I'm going to use my general term up there. So I've got n, which is 13, choose r, times my a value, which is x cubed, to the n minus r, okay, which is 4. And then I've got 2x to the 9. Expanding all that out should give you that your 10th term is 366,080 with the exponent x to the 21. The examples about Pascal's triangle you can see in the hard copy of the note that's posted in our unit outline.